Okay, so now let's look what happens with what's called the modified Euler method. Or oftentimes referred to as backward Euler. Okay, so let's consider the sort of modified Euler method. Which is given as follows. Xn plus 1 is equal to xn plus h times f evaluated at tn plus 1, xn plus 1. Okay, and then when you apply this, when this is applied to the model problem, x prime is equal to lambda x, and x at 0 is 1. Right, we obtain just that xn is equal to, xn plus 1 is equal to xn plus h lambda xn plus 1. Okay, so I can solve for xn plus 1. So I get xn plus 1 multiplied into 1 minus h lambda is equal to xn. All right, so xn plus 1 is equal to 1 over 1 minus h lambda, right, times xn, which means that xn is equal to 1 over 1 minus h lambda, right, to the nth power. Okay, because x0 is 1. Okay, so so let's look back again at the situation. It's like which we had, where we want to consider sort of the situation where lambda is negative, right? So again, when lambda is negative, well, you know that this solution looks like x of t is equal to e to the lambda t, right? So when lambda is negative, it's like you have an exponentially decaying solution, which goes to 0. So you want, it's like the numerical solution, it's like to go to 0 as well. So consider a situation where lambda is less than 0, then we want that the absolute value 1 over 1 minus h lambda is less than 1. All right, and you can easily convince yourself that this is true, which is true whenever h is greater than 0, because if h is greater than 0, lambda is negative, then minus h times lambda is positive, so this is 1 divided by 1 plus some positive number, which obviously is less than 1 in absolute value. Okay, so this again is true. It's like whenever h is greater than 0. So in contrast to the usual Euler method, when applied to this model problem for lambda is negative, right? So if you recall, with the usual Euler method, it's like you have a step size restriction that the step size cannot be larger than minus 2 over lambda. All right, and if you took a step size which was larger than that, then what would end up happening is that the numerical solution would end up, it's like exploding, right, as opposed to decaying to 0, right? But with the modified Euler method, or what is sometimes referred to as the backward Euler method, right, then as long as you take a positive time step, right, then the numerical solution is always going to decay to 0 so long as lambda is negative, right, which is exactly the situation where the continuous solution decays. So all that makes perfect sense. Okay, so so the remark is that in contrast to the usual Euler method, right, the modified Euler method can take sort of arbitrarily large time steps without the numerical solution exploding. out the numerical solution diverging when lambda is greater than 0. Okay, so so that's kind of an interesting phenomena. So so that's again sort of an example. It's like of a slight modification to a well-known numerical method. It's like which allows it to in principle perform better. It's like for a problem like this, it's like which is sort of a prototype of what happens. It's like in a stiff problem. Okay, so so where it really gets interesting is when you have systems of equations. Again, as I said, it's like with multiple time scales. But this is sort of an indication that even in a scalar differential equation, it's like sort of shadows of what is going to be, you know, it's like this issue. It's like with stiffness, it's like manifest themselves in some methods and not in others. Okay, so let's look at this more. It's like in a little bit.